Alright, welcome to Chapter 3, Section 7 of Math 330, Differential Equations. We're going to talk about electrical circuits. Electrical circuits can also produce non-homogeneous differential equations, so we're going to look at some. So basically, we treat this as another application for non-homogeneous differential equations. Remember our damped harmonic oscillator that we had earlier that was driven with some function f of t. If we get a circuit that looks like this, where C is a capacitor, L is an inductor, and R is resistor, E is the voltage source, what we can do is, what we're going to do is claim that the current is the derivative of the charge with respect to time, and then the voltage drop across the inductor is equal to this. The voltage drop across the resistor is equal to this, and the voltage drop across the capacitor is equal to that. So if we do that, and then we'll have some power source that changes in time here. So if we do that, and then if we go around this complete loop here, add up all the elements in there, that has to equal to the voltage drop across the power supply. So we've got the voltage drop across the inductor, the voltage drop across the resistor, and the voltage drop across the capacitor. And this gives us another differential equation. But the problem is we have a derivative with respect to I here and a Q here. So we need to relate them. There's two ways of doing that. We can take the derivative of the whole equation, and when we do that, the derivative of the charge with respect to time is the current. So now we have a second order differential equation with respect to the current. Or we can plug in that I is equal to the derivative of the charge, and then we have a second order derivative with respect to the charge. So there's two ways of solving these problems depending on if you want their charge or if you want the current. And if you have one, you can always get the other by looking at this. Alright, so let's do an example. Let's look at problem 2 on page 215. It says, given the same circuit in problem 1, which is this circuit right here, suppose that the switch is initially in this position and it gets thrown to this position, position 1, at t equals 0, so the current is equal to 0 at t equals 0, and the E is equal to 100 for t greater than 0. Find the current and show that the current goes to 4 as t goes to infinity. Okay, so here's our differential equation. But in this case, we have no Q. We just have an L and an R. And then our L is 5. You find that from problem 1. And the R is 25. That's in problem 1. But our E is 100. So the Q, the problem with Q disappears. And all we have is Ri and an L di dt. So we have a first order differential equation with respect to current. So we're going to solve it and manipulate it in terms of a first order differential equation, and we get this. So we integrate both sides. We're going to get this, and then the integral of that is equal to this, and then take the exponential both sides. I get that. And then I apply the property of exponents. I get this, where c times the e power is still a constant. And I'm going to write that constant as I0. So this constant and this constant are the same thing. Well, if I solve for I get this expression, and at t equals 0, current is 0, e to the 0 is 1. So if I solve this, I get I0 is equal to 4, and I plug that back in, I get this is my current, and that's what they wanted us to find. Now, as t gets very, very large, okay, e to the minus large number is small, so this term disappears, and the current goes to 4. Alright, let's look at another equation, or another problem, I should say. It says, suppose this circuit right here, where R equals 200, and the capacitance is equal to 2.5 times 10 to the minus 4. At t equals 0, Q is 0. The power source is equal to this. So it's 100 times the cosine of 120 times t. We want to find the charge in the circuit as a function of time, and the current in the circuit as a function of time, and then we want to find the amplitude of the steady state current. So here's our standard differential equation that you start out with each time, but in this case, this term right here is equal to 0, and so that goes away, and then I put in the definition of I is the change in charge with respect to time, R is 200, C is this value, and E is this value. So I got another first order differential equation, but this one is not a separable one like earlier. This is one of the standard form, or using the integrating factor. And so do some more math, and this is the differential equation we need to solve. So my integrating factor is e to the 20 times t, and then that's going to turn this differential equation, if I multiply by e, into this one. Alright, so now it's a separable differential equation, and I need to integrate it. So I integrate the left-hand side, that easy, but the right-hand side's a little trickier. So I'm going to write this way and factor out the 1/2, and what I'm interested in is this integral. So what I'm going to do is that integral. To do that integral, I have to do a u substitution, where, I got to integrate by parts. So this is my u, this is my dv. That gives me a du of this, a v of this, and then if I plug it in to do the integral, I get that integral has to equal this, and that gives me this integral that I have to integrate by parts again. So my new u and my u dv is this, my dv, my du, and my v is that. I plug that back in. What I'm going to get is this answer. But you see, this term shows up, and that's what we initially had back in this integral. So this is going to allow me to bring it over to this side of the equation. And I have this expression here, where I can factor out my integral. It's in both terms. And I'm left with the integral times some constant, in this case 37. So what I can do is now I have this. Well, now I have the integral I was looking for, and I can plug it back into here. All I have to do is multiply this by 1/2, and if I do that, I get this expression. So now I have that expression, and I just have to solve for q. So now all I have to do is divide by this through the whole expression, and I get my q as this. Well, I got to find my initial condition. Well, at t equals 0, q equals 0. Sine of 0 is 0. E to the 0 is 1, so I get this. So d has to equal negative 1 over 1,480. Plug that back into my differential equation, or my solution to my differential equation. Here's my charge with respect to time. Now if I take the derivative of that, with respect to time, I get the current. If you do that, you get your current. Now, part B wants to know what is the amplitude of my steady state current. Well, as time goes on, gets very large, this term is going to go to 0. That's the transient part of this equation. And this is my steady state current. Well, it wants the amplitude. I don't have that. I have to apply this trig identity again. And if I do that, I find out that C sine phi is equal to a minus 3/37. And I find out that C cosine phi is equal to 18/37. And I divide those two, and I get the tangent of phi has to equal to a -6. And if I solve for phi, I find out it has to be a negative 0.0515 radians. Let's make sure everybody knows this is a radian, not degrees. And then I can take that, plug it back in, and find my C, and I find out my C is a little bit larger than a half, and that is my steady state amplitude, or the amplitude of my steady state current is a 0.51423 amps. The current would be amps. Alright, so, well, that's the end. I hope you get a better idea how to solve these equations. We didn't solve any really second-order differential equations yet. We'll work some more in class. And I'll see you in class. Bye.